So I would like to thank the organizer of this FDP program, and particularly to Professor Prasanth Panigrahi for the invitation, and also to Professor Rao. So we will start the presentation, and as you can see, the title of this presentation is Sensing with Heralded Single-Photon Spectroscopy. This is somewhat related to quantum sensing because we will use single photons, quantum light for the sensing application. So intentionally, I have made this presentation very simple because this is a faculty development program. So the intention of this talk is to familiarize these participants, and I assume that the participants are from different universities and institutes, faculty members, and also few research scholars. So I will present the basics first, and then I will use these basics to give a sensing application for a particular case which you have realized in our lab. And also I will give some future scope of this work. In fact, we have recently set up a lab for the quantum sensors, particularly using this heralded single photons. And we have modified the setup for different sensing applications. Before going to my talk, let me just introduce before you the works which you are doing in our center. As Professor Rao introduced me as the director of the Center of Excellence for Nanoscience and Technology for Development of Sensor. In fact, this is a Center of Excellence which was founded by this government of Odisha Department of Higher Education. And we have actually different projects in the center, and also we work in different areas. And as you can see, the 50% work is based on sensing, and out of this sensing, as you can mark, maximum chunk of work is classical sensing. We work in fiber optic sensors, and we have designed maybe more than a dozen of fiber optic sensors for different applications. And after doing a number of works in quantum sensing, and in fact, Professor Panigrahi boosted me to start, something in quantum sensing. So recently, in the last 2 years, we have started working in quantum sensing. So this is also another area where I will talk today. Besides this sensing, we also work in other areas like water treatment, surface engineering, and energy harvesting, particularly third generation.
Sorry, could you press on the hide button, please?
Okay. Now, is it all right?
Yes, thank you.
Okay. And just to give you some idea about what are the different prototypes we have developed, though these prototypes are not related to this talk, particularly this is a non-invasive H1C detection kit. We can measure your H1C level by this kit. And these are some other prototypes we have developed, but this prototype which we have developed recently for secure communication with quantum entropy is something related to this experimental setup, which I will discuss today. So this is, in fact, a prototype which we have developed for quantum random number generators. So with this brief idea about my center, let me go to my talk, and this is plan of my talk. As you can see, we will start with the basic idea about this optical sensing. We can say classical sensing, and gradually we will try to understand what is the difference between classical and quantum sensing. And after that, we will see the single photon sources may be used as a source for this quantum sensing application. And we will discuss about the different methods by which you can produce single photons thereafter. One of the important experimental setup by which you can produce single photon is due to a nonlinear process, which is known as spontaneous parametric down conversion. And I will speak something about this spontaneous parametric down conversion. And after discussing basics of spontaneous parametric down conversion, I will go to this experiment, where we produce a spontaneous parametric down conversion process and produce heralded single photons. And with this experimental setup, we will also explain once you have produced some light, and you have to verify that the light which you have produced is of quantum nature. So what are the different processes by which you can verify that the light which you have produced are really quantum in nature? So this is what is called the verification of quantum nature light. And once you have discussed about some of the basics of this quantum nature of light, how to produce single photon, we will take a simple example like how to sense acetone by using this heralded single photon spectroscopy. And we will also show that this heralded single photon spectroscopy, which rely on the principle of quantum mechanics, is something better than its classical counterpart. So with these ideas about this classical quantum sensing, we will also explain some of these recent experiments which you have conducted in our lab, like single and two photon interferometry, and how this single and two photon interferometry can be used for also sensing applications. This is what I will talk in this total lecture. Now, starting with this optical sensing, as you know, sensing means to measure or detect a physical quantity. The physical quantity may be anything like temperature, pressure, stress, strain, or any biological parameters. So this is the physical quantity which you have to measure. And if it is optical sensing, then you have to use a light source and a detector for the sensing setup. And the basic principle is explained in this diagram. If you will see this diagram, there is a source here and there is a detector here. And this power which is emitted from the source is Pi. And let us assume that the power which is received at this detector is Ps. So the power which is received at the detector, Ps, is related to this power which is emitted from this source, Pi, by this relation which is mentioned here. And this eta is basically the coupling efficiency, including the source and the detector. And if there is nothing between the source and the detector, it may be also air medium. So this is also possible to have a sensor, but in our applications, we use an optical fiber to connect between the source and the fiber. So this cylinder which we are showing here is something, an optical fiber, which will connect between the source and the fiber, so that the light can be guided and can be reached to this detector. Then if you will consider this optical fiber, then there are some other parameters which will decide what is the power which is received at the detector. For example, the transmission efficiency and the responsivity of the detector and all. So if you'll assume that the source, detector, and the fiber are constant, we are not changing those source, fiber, and detector, then this eta, T, and R will be constant. So therefore, this power which is received at the source basically is decided by this M. So the M here is actually the measurand, the physical quantity which you want to measure. For example, if I want to measure temperature, temperature is the measurand. If I want to measure pressure, pressure is the measurand. So M is in general measurand which you want to measure. So the measurand, as you can see here, is a function of intensity or phase or wavelength or polarization. That means the power which is received at this detector can change with respect to intensity, with respect to phase, with respect to wavelength, or with respect to polarization. So based on that, the sensors are classified into different types, like if this detector output, the output at the detector changes with intensity, this is called the intensity modulated sensor. Similarly, if this is with respect to phase, this is phase modulated sensor. And similarly, the spectrally modulated sensor, if it changes with wavelength, and polarization based sensor, it changes with polarization. So this is the basic principle of all sensors, all optical sensors. And in general, I'm talking about this optical fiber sensor because this optical fiber is connecting between the source and the detector. Now, what we'll do next, what is the basic principle by which you can measure the unknown parameter or the measurand? You apply different measurement here on a small portion of this optical fiber, for example. So if you will apply, different physical, I mean different, for example, I want to measure temperature. Temperature is a measurement here, and if you are applying different temperatures, then definitely the output at the detector will change with respect to this temperature. So we have to then plot a graph between this temperature, because temperature is the measurement here, and the output which you are getting at the detector. So you will get a like a linear graph, and if it is not linear, of course, you cannot use this for sensing applications. So once you have plotted this calibration graph, then your setup is ready for measuring any unknown parameter. For example, if you have this calibration plot after measuring the output at the detector for different values of temperature, now you apply an unknown temperature and you can find what is this detector output, and from the detector output I can find what is this unknown temperature from this calibration graph. So this is the basic principle of almost all these fiber optic sensors. And as I have said, the source which I have used here is a light source, laser source, tunable light source, basically, for example, a laser source. Now, if you will use a laser source, which is assumed to be a source which is not quantum in nature, so therefore, if I want to, you know, try to find the performance of this sensor, then what are the parameters which I want to measure? So the different parameters which you want to measure for a good quality sensors are sensitivity, limit of detection, specificity, response and recovery time, and temperature dependence. So once you have designed a sensor, the immediate thing which you have to do is to find its sensitivity. So sensitivity you can find from this calibration graph. If you find the slope of this calibration graph, this will give you the sensitivity. And once you know the sensitivity, you can find also the limit of detection, which is the lowest amount of the physical quantity which you can measure using this sensor. And as you can see in this relation, this limit of detection can be calculated from the sensitivity and also this variance, this standard deviation. So once you know the standard deviation and the sensitivity, then you can calculate this limit of detection. So the sensitivity and limit of detection are must for all the sensors. That means you have to find what is the sensitivity of the sensor, what is the limit of detection of the sensor. The other parameters which are equally important for any sensors are specificity, response and recovery time, and temperature dependence. That means suppose we want to measure a particular physical quantity. Let us give an example here. For example, I want to measure acetone. If I want to measure acetone, then you have to see whether this sensor is also responding to the similar interfering species to that of acetone. Because besides acetone, there may be also other interfering species similar to this acetone which may be present. So your sensors should not be sensitive to the other similar interfering species similar to acetone. So that you have to verify that your sensor is not responding to any similar interfering species to the measurement or to the physical quantity which you want to measure. And similarly, you have to also find the response and recovery time. Response time means what is the time, the duration of the sensor which will take to reach the 90% of its final value. And similarly, recovery time is how long it takes to return to the 10% of the baseline value. So the last parameter which is also important is the temperature dependence, because if you are measuring this physical quantity and suppose there is a variation in temperature in the environment, your sensor performance parameters should not change. For example, sensitivity should not change, limit of detection should not change. So you should also ensure that the sensor which you have designed should not vary these different parameters, the different performance parameters should not change with respect to temperature. So these are some of these parameters which you have to find for any sensor you have designed. Now, the problem is if you will use a source, as I have mentioned in this first slide, that I have to use a laser source. Now, if I will use a ledger source, then is there any demerits with this ledger source? So there are few demerits of this ledger source which can be, which you can get rid of by using this single photon sources. So in this slide, I have mentioned what are the different possible demerits in ledger source and how you can, get rid of that using this single photon source. Now, if you say this is ledger source, basically it satisfies this Poisson's distributions of emission of photons, whereas single photon source will satisfy soft Poisson's distributions. So when I say soft Poisson's distribution, that means the fluctuation of photon number should be equal to this mean value of these photons which are emitted. Whereas in soft Poisson's source, like a single photon source, this fluctuation is less than this average number of square root of average number of photons. So these statistics should in fact verify to check whether your source is a classical source or a source is a quantum source. So this is the first thing you have to do when you will produce, for example, single photon source. Now, if you have a classical source like a ledger source, there will be a noise level which is sort of standard short noise, whereas in case of your single photon source, this will be below short noise. This is one of the merit which we'll get in case of single photon source. And similarly, another important parameter which you can get in case of single photon source is the error. The error which you will get in your classical source, for example, if you use a ledger source, is something equal to 1 by root of n, where n is this number of photons. And in case of your single photon source, the error will be 1 divided by n. And as the denominator is more in case of single photon sources, therefore you will definitely get the error will be less in case of your single photon source. And another important parameter which you can see is the signal to noise ratio, because signal to noise ratio is a very important parameter for any sensing application. And the signal to noise ratio is basically decided by this ratio, that is the average photon number divided by this root of n. Whereas if it is your quantum source or the single photon source, then this is less than of root of n. So because the numerator is same in both the cases and the denominator here is something less, therefore the signal to noise ratio in case of signal to noise ratio for single photon source will be more than that of this classical source of the ledger source. So by saying this, we understood that if you can use, you can replace this ledger source by a single photon source, then you can get some of these merits, like SNR will be very high, this error will be minimized, so that the sensing performance can improve. In fact, the limit of detection can improve compared to this classical ledger source if you use this single photon source. Then the next question which comes into mind is whether this photon number which we are producing in case of single photon is important. Because I said that if you will use single photon source instead of this classical ledger source, then the SNR, then the limit of detection can be improved by a considerable amount. Then the question is what should be the number of photons, whether this number of photons is important or not. In fact, the number of photons is also equally important, because if you see this relation, the error basically is decided by root of n and n. Because if n is equal to 1, for example, then there will be no difference, because 1 by root of 1 or 1, so there will be no difference. So therefore, if you will use only n is equal to 1 in this experiment, then there will be no difference between this classical sensing and this quantum sensing. Therefore, you have to increase this number of n, or the number of photons in your experiment. The minimum value of n, if you have to use, is n is equal to 2, so that you can improve this sensitivity, limit of detection, and SNR. So this is also important, that you have to use a minimum 2 photons in your experiment, so that you can improve this limit of detection and sensitivity, and also your SNR. Now, for that, what you are doing in our experiment, we use a nonlinear process called as spontaneous parametric down conversion, which I will explain a little later, and we produce two photons. And these two photons are known as signal and adder. So basically, you use n is equal to T2 in our experiment and try to improve the sensitivity and also limit of detection and improve this SNR. So the two processes which are important and we have to understand is, as I said, is spontaneous parametric down conversion. And as I mentioned, this is a nonlinear optical process where you have to use a pump signal and use a nonlinear crystals like BBO or PPKTP or lithium niobate. And this nonlinear crystals, when excited with this pump, then it will produce two photons, down converted photons in fact. So these down converted photons will have lower energy, and these down converted photons are called as signal and adder. We will explain about this SPTC in detail after some time. And another important thing which also you have to understand is the heralded single photon means if you produce, for example, signal and adder, two down converted photons, and if you can detect one photon in one detector, then the other photon should be guaranteed. So this is what is called the heralded single photon. You can herald a photon with the presence of these other photons or the other detector. So this is how we can distinguish between this quantum sensing and classical sensing. As you have already mentioned, if you have a classical sensor, you should have some laser source, which is not a quantum source like this. This will not exhibit any quantum property, and you have a detector and you have a sample. So the sample will interact with this light, and after the interaction, you can measure this detector output. And based on this detector output with this interaction of the sample with this measurand, you can have a calibration, and from that calibration you can find different parameters. And in quantum sensing, what is the difference? As you can see, instead of this laser source, I am using something like a heralded single photon source. Means you have a pump laser here, and you have a nonlinear crystal here, and the pump will excite this nonlinear crystal. As a result, you will get two photons, the down converted photons. Say, for example, this is the signal photons, this is the ideal photons, and these signal photons and ideal photons will be fed to detector, and you can herald a photon with the presence of the other photon. For example, if you can measure this photon here, then in one of the detector, then the photon must be there in the other detector. So that means if the photon will click at the one detector, the other photon must click at the other detector. That means one photon is heralding with this other. So in this setup, for example, you are using this sample. You can see the difference here. You are putting a sample in between the source and the detector, whereas here what you have to do is you have to put the sample in one of this photon. For example, if you say that this is the signal photon, this is the ideal photon, this signal photon is going to this detector without any interaction, whereas this this ideal photon is going to this detector without any interaction, whereas the signal photon is going through the sample after interaction to this detector. And therefore, if you can measure the coincidence between these two photons, then you can calibrate this, the concentration or the measurement with respect to this coincidence count. So the coincidence count means, suppose one photon clicks here and one photon clicks at the same time, then you will say that there is a coincidence between these two photons. And for example, you have allowed 100 photons. How many photons click at the same time between these two detectors will give you the coincidence count. For example, out of 100, for example, 80 photons clicked at the same time at the two detectors, the coincidence count is 80. And suppose here I have not put any sample and the coincidence count is, for example, 80. And now you put the sample here, definitely the coincidence count will change. And with this variation of this parameter, for example, if I will change this concentration of some sample here, definitely the coincidence count will change. and therefore you can calibrate between the coincidence count and the measurand or the quantity which you want to measure. So this is how this quantum sensing is different from the classical sensing. What you are doing here is you are using some principle of quantum mechanics for this measurement, but not you are measuring this intensity of power. As you can see in classical sensing, you are measuring basically power, the intensity, and you are calibrating with respect to this intensity and power. Whereas here you are not doing that. You are calibrating in terms of some quantum mechanical parameter using some quantum mechanical principle. Now coming to the definition, formal definition of this quantum sensor, you can see that these are the different approaches where you can classify this different quantum sensor. And the formal definition of quantum sensor may be like this: use of quantum systems as probes to measure physical quantities with enhanced sensitivity and precision. If you use, for example, quantum object like single-atom, trapped ion, or NV center as probes, this will be termed as quantum sensor. And if you use, for example, quantum coherence, like exploiting spatial and temporal superposition states, this will be regarded as quantum sensor. And if you use this quantum entanglement, using entangled states to improve this sensitivity and precision, then this will be also regarded as quantum sensors. So therefore, some of the quantum sensors which are widely used are atomic clocks, which are used for resonant frequency with microwave lasers, atomic interferometer, optical magnetometer, Rydberg atoms, and all these are well known in quantum sensing areas. And the key quantum resources are superpositions, entanglement, and squeeze states. So in this presentation, I will go something beyond this. I will not discuss about the quantum sensor which I mentioned in these slides, but I will present something different sensor which is based on the principle of correlation or entanglement. Of course, this can be also extended to superposition states by using this two-photon interferometry. You can also extend this to squeeze states. But in this presentation, I will restrict to what is called as the correlation between these two photons, and how this correlation between two photons, how the heralded spectra can give rise to some quantum sensing applications. This is what we will do here. Now, there are different methods by which you can produce these single photons, and there are few of these methods which are mentioned in these slides. One is your NV centers, nitrogen vacancies, quantum dots, and SPDC. And this is what I will explain in this presentation: spontaneous parametric down conversion, and how to produce these single photons using this SPDC, and how to use them for sensing application. This is what we are going to trying to understand. This is actually the basic principle of spontaneous parametric down conversion. As you can see here, there is a nonlinear crystal, and there is a pump signal here. And when this pump signal is incident on this nonlinear crystal, there is a interaction. A nonlinear interaction will be there, and you will get these two down converted photons, and these two down converted photons are known as signal and ideal. And this should satisfy this momentum conservation as well as the energy conservation, as you can see here. And the nonlinear crystal which you can use here maybe like a beta barium borate, potassium titanyl phosphate, or lithium. These are some of the examples of nonlinear crystal you can use to produce this SPDC. But in our experiment, we have used KTP for producing these spontaneous parametric down converted photons. Now, there are various types of SPDC, like type 1, type 2, also type 0 is there. But you can see the difference between this type 1 and type 2 SPDC. This is basically the blue one is the pump, and the red one, as you can see, are the signal and the ideal. Now, if you see here, for the type 1 SPDC, you are getting two concentric cones. That means the light which is emitted after this interaction out of this nonlinear crystal will have the light cones, as you can see, are concentric in nature. Whereas in type 2, there is an angle between this cone. So they are making some angle between this direction of the pump. So therefore the cones are slightly twisted. And if you see this polarization here, the polarization of the signal and idealer are same, but this is something opposite to the polarization of the pump. So if this pump is horizontal polarized, then the signal and idealer are vertical polarized. Whereas in type 2 SPDC, as you can see here, this is your pump. That means if the pump is horizontal polarized, then as you can see, the signal, for example, is let us say vertical polarized, then the idealer is horizontal polarized. That means they are not on the same polarization, whereas here they are in the same polarization, they are not in the same polarization. So this is the difference between type 1, type 2 SPDC. And in our experiment, we have used this type 2 SPDC to realize these sensing applications. Now, a simple KTP crystal cannot give you an intense beam of signal and idealer. So therefore, you have to take a PPKT, that is periodic polling of this KTP crystal. So if you have a periodic polling of this KTP crystal, then what will happen is due to this chromatic dispersion, this wave vector will actually change. So the direction of this signal will change, and therefore when the signal and the idealer and the pump, they are traveling in this crystal, you will see that after some time the signal and idealer will be lost and you will not get any intense beam after this crystal. So therefore you have to periodically pole this KTP crystal so that there will be compensation. And when it is twisting, actually if you see the difference between these two here, if you are not giving a periodic polling, then this change in the phase will be such that you will not get any light after coming out of this KTP crystal. Whereas in this case, where there is a periodic polling, then what will happen is the light will come out, intense light will come out, because the change in this direction will be compensated, because as you can see the direction of the nonlinearity are reversed in those cases. And this is actually called as the quasi-phase matching condition, because in case of type 2 the phase matching condition is something like K pump is equal to K signal plus Ki plus some delta Kz, so that the quasi-phase matching condition will be satisfied in case of PPKTP. And the main aim of this is to get an intense beam of signal and idealer. So if you simply take a KTP crystal, you will not get any intense beam after this nonlinear interaction. But if you will take a periodic pole KTP, then you will get an intense beam. So this is actually the diagrammatic representation. This is the PPKTP crystal, where you will get an intense beam out of this crystal due to this quasi-phase matching condition. And you can also see that this phase matching condition, which is mentioned here, depends on various parameters like temperature, wavelength, angle, and phase. That means you can also change this emission from this PPKTP crystal, for example, by varying those parameters. For example, temperature. If you can change the temperature, the wavelength which is emitted from this PPKTP crystal will change. So this is in brief about this KTP crystal and PPKTP crystal, which will produce actually two down converted photons like signal and idealer. And as I mentioned, we have used a PPKTP crystal and try to get the signal photon, ideal photon, and use them for sensing application. What are the different components we will use for this experimental setup? I have mentioned the different components which I have used in our experiment. The first one is a pump laser source. The wavelength of this is 405 nanometer with a tunable power of, it can go up to 50 milliwatt. It can go from 2 milliwatt to 50 milliwatt, 1 milliwatt to 50 milliwatt. And the nonlinear crystal, as I mentioned, PPKTP crystal. This is a 10 millimeter long PPKTP crystal. The periodic polling is 10 micrometer, and the aperture is 1.1 cross 2 millimeter square. And this will give you some down converted photon of wavelength 810 nanometer. That means if you will pump this PPKTP with 405 nanometer, it will give you signal and idealer with approximately 810 nanometer. Of course, if you will maintain the temperature at 30 degrees centigrade, and also the pump power is maintained at 2 milliwatt. If you change the temperature, the wavelength will also change. You also need single photon counting module, because the detector which will use for this are very sensitive. You should count the number of photons which are received at the detector. So you have to use some single photon counting module. You have to use a time tagger which will measure the coincidence count. And other component which I also use is polarizing beam splitter, filters, half wave plate, polarizing, maintaining optical fiber. This is important because when the signal or idealer is passing through an optical fiber, it should not change its polarization. Therefore, you have to change this polarizing, maintaining optical fiber, temperature control ovens, and also number of lenses, mirrors, and iris for mounting this mounting on this honeycomb table to steer the beam to a particular direction. So this is actually the heralded single photon setup which you have used in our laboratory. Let us see how it works. This is actually the 405 pump laser source, continuous laser source, and this is actually this will produce vertical polarized beam. And the PPKTB crystal in fact needs a horizontal beam for the excitation. So this vertical polarization will be converted to this horizontal polarization by using this half wave plate, and then it will be sent to this polarizing beam splitter. So if any vertical components are there due to some experimental errors, then this can be filtered by this. So the vertical components will be coming in this direction, and this will be blocked, of course, and therefore only the horizontal component will pass through this, and this horizontal component of this will be pumped to this PPKTP crystal. And when this will be pumped to this PPKTP crystal, then as you can see, there will be two photons which will be produced. These are the two down converted photons known as signal and the idealer. And you can use another polarizing beam splitter to separate them, to separate the signal and idealer. As you can see, the signal is horizontally polarized, and the idealer is vertical polarized, as I mentioned. This opposite polarization confirms this, this is a type 2 SPDC, because the polarizations are not same. So once you got this horizontal polarization and vertical polarization, you just take them through two polarizing maintaining fiber. So these are some of these polarizing maintaining fiber. And then you can feed this to this single photon counting module. SPCM stands for single photon counting module. And these are the polarizing maintaining fiber. So once you have connected this signal and idealer to this SPCM, then they can count the number of photons which are coming to this. All right. So say for example, if you say that one photon clicks here at this detector, then the other photon should click at this detector, because these are the signal and idealer. And if you are ensuring that one photon clicks here, then it will be ensured that this other photon will also click here. Therefore, these are the two heralded single photons which are producing at these two different ends. And once you have produced these photons, and you have to use this coincidence count or the time tagger, which will measure the coincidence count. How many photons will click at the same time in a given time beam, and that will be connected to a computer where there is a software, and you can plot the spectra of the coincidence count. That means you can have in the x-axis this time delay, and in the y-axis this coincidence count, and from that you can confirm whether you are getting this heralded single photons or not. And these are some of these experimental results. The pair generation is at this rate of the order of 10 to the power 5 pairs per second. This is the heralded efficiency, 60%, and this is the G2 factor, which is to be less than 1 for this quantum source or the quantum nature of light. So it is something 0.023, which confirms this quantum nature of light, and this Mendel Q parameter is calculated this. That means these are some of the parameters which you have to calculate so as to ensure that the light which you have produced in this setup is quantum in nature. Now, just a minute. Okay, this is actually the experimental setup. As you can see, this is the continuous wave laser source, pump laser source, and this is actually the PPK-TP crystal, which is connected to a temperature source. In fact, if you can vary the temperature, the wavelength of emission here also can be changed depending on the requirement. And out of this, your PPK-TP crystal, you will get signal and idealer. These are two single photon counting module where the signal and ideal photons will be fed, and these two will be connected to this time tagger, which will measure the coincidence count, and this will be measured in this system, which is have a own software. Right. So this window shows the number of the ideal photon and signal photons. This is actually the signal photons which are getting, and this is the ideal photon which are getting. So the number of photons, of course, are not same. So this is this is actually biased. So that means more number of photons are coming in this signal, and the less number of photons are coming in the ideal. But you are getting some photons. But what is important here is you have to ensure that the photons which are produced is heralded in nature. So for that, you have to actually plot it this. So this is actually the delay versus this coincidence count. As you can see, at time delay is equal to 0, you are getting this maximum peak here. So this is actually the signature of the heralded signal photon. If you are getting a maximum peak here, that means this photon are reaching simultaneously at the two detectors at time delay is equal to 0, which shows that this is heralding in nature. Of course, in your single photon, if it is purely a single photon, you will get 0 here, because if one photon reaches the detector, the other photon will not reach the other detectors. In that case, you will get 0 coincidence at a time delay is equal to 0. But because this is heralded single photons, the two photons will reach at these two detectors simultaneously. Therefore, you will get maximum coincidence here, and as time delay increases, it will decrease and finally reduce to 0. So this is how the experimental setup is performed for heralded single photons. And as I have mentioned that once you have produced the light from this PPK-TP crystal, then you have to calculate some of the parameters to ensure that this nature of light is really heralded or quantum in nature. So these are some of the parameters which I have already mentioned in the previous slide. You have to calculate the Mendel Q parameter. This is the formula you can use to calculate the Mendel Q parameter. Similarly, you have to calculate the second order correlation at a time delay is equal to 0. And if you can calculate these parameters, and if you find that Q, that is the Mendel Q parameter, is less than 0, then it will signify shock Poisson's distribution. That means quantum nature of light. If it is equal to 0, Poisson's statistics, it will not showing quantum nature. This will be a laser source. And if it Q is greater than, this is super Poisson statistics. So these correspond to different nature of light. For example, if it is similarly, you can calculate also the second order correlation function for this quantum nature of light. As you can see, if this G20 is 0, this will produce ideally single photons, and if it is less than 1, this is quantum. Equal to 1, coherent, like a laser source. Greater than 1, this is the thermal source. So this is what we have calculated in the last slide I have mentioned. So this is what we have calculated, G20 factor and Mendel Q parameter, and the value which you got really confirms that the photons which are produced is quantum, the light which are produced is really quantum in nature. And for sensing, you have to calculate this quantum Fisher information, and once you have this quantum Fisher information, you can calculate what should be the minimum precision measurement that can be done by using that particular sensor setup. And as you can see, this is how you can calculate the Fisher information. And once you can calculate this Fisher information, then you can calculate this CR bound, and the CR bound actually will give you an idea about what is the minimum measurement of this physical quantity you can make using this sensing setup. And as you can see, the Fisher information basically depends on this RC, the coincidence count in terms of concentration. So you have to calculate this first, and then you have to decide what should be the minimum, uh, parameter or minimum amount which you can measure for a particular physical quantity. And your experimental measurement should not be less than that. So this is also how you can predict what is the minimum measurement you can make, or what is the limit of detection which you will get in a particular sensing application theoretically, and then you can try to achieve this experimentally. Now, having said all these things, basics things, let me give a particular example which you have realized in our lab to ensure that yes, if you are using this quantum principle for sensing application, then really this performance of the sensor is enhanced. So to go to this quantum sensing, I will take some time to explain about the classical counterpart. In fact, this setup is for a classical sensor to measure acetone concentration. Why you are interested in acetone concentration is something different, because acetone actually we try to measure from the axial breadth. The amount of acetone which is present in the axial breadth is important, because it can diagnose your diabetes. If this concentration of acetone in the axial breadth is between 0.2 to 0.9 ppm, then you are safe. And if it is more than 0.9 ppm, then you are suffering from diabetes. So therefore, you have to measure the concentration in the axial breadth if you can, if you want to measure, whether you are suffering from diabetics or not. So the minimum measurement which you want for this sensing application, as I mentioned, is 0.2 ppm, because the safe limit is from 0.2 ppm to 0.9 ppm. If it is more than 0.9, then pre-diabetics. If it is 1.8 ppm, then you are suffering from diabetics. So you have to consult a doctor, something like that. So here is an experiment which we have performed in our lab. This is not actually a classical sensing setup. Quantum sensing setup. This is a classical sensing setup. And I will not go into detail of this, but I will mention that this is again a optical fiber sensor based on some nanomaterial coating. And in this nanomaterial coating, we have used some material. I will not go to this detail of this. So
sir,
we have used some material.
Sir, excuse me, sir.
Sorry. Yes.
Sir, actually, please take another 5 minutes, so that last 5 minutes will be for question answers.
Okay. I will conclude. So I will not take much time. So let me just mention here that using this classical sensor setup, the minimum amount of acetone concentration you can measure is 0.63 ppm. That means it is not reaching to 0.2 ppm. So therefore, if I want to use this for sensing application, particularly for diabetics, you have to reduce this limit of detection 0.63 at least to 0.2 ppm. So this is not possible if you use classical sensing setup. So therefore, I have gone for a quantum sensing principle using this heralded single photon spectroscopy. And this is the setup we have used. And as I have mentioned, I have used SPDC and heralded single photon, and I have tried to measure the concentration of acetone. Now, if I will measure this concentration of acetone, then the limit of detection which we have found is something 0.213 ppm. I will not actually take, because these are some of the mathematical principle based on which this sensing principle will work. Heralded efficiency I have mentioned, and also I have mentioned this Q value, so that I have confirmed this quantum nature of light. And I have also calculated the quantum Fisher information of that particular sensor, and I have said that the quantum Kramer inequality value is 0.0258 ppm. That means I can go down to this limit of detection up to 0.0258 ppm if I use this principle. This is found from this theoretical calculation, and experimentally what you found is the limit of detection is 0.213 ppm. So this is how we have reduced this limit of detection by using this heralded single photon spectroscopy. These are some of this, like calibration plot. This calibration plot is with respect to this, Abdul HM of this coincidence, and this is with respect to the coincidence count. So these are different calibration curve, and in fact, these are the signal and radial photons which are getting, and this is actually the signature of these heralded single photons. And if you vary the concentration, in fact, this will also change. And we have measured this Abdul HM, how it changes with the concentration. Then you have measured this, calibration plot. So these are some of these calibration plot in different, principles. Like this is based on Abdul HM of coincidence, and this is based on simply coincidence count. So what I want to mention here is that if you can use this quantum principles to measure instead of this like intensity and power, then the limit of detection and sensitivity can be enhanced much more than this classical center counterpart. Just I will wind up by saying two of these slides. So this is another configuration where we have used single photon interferometry for sensing application. In fact, if you see this graph, this black one is the theoretical one and the red dots are the experimental one. And we have realized that the single photon interferometry is realized in this particular setup. It should obey P2 is equal to cos square 5/2, and experiment also is showing something similar to that. And you can also use this setup for sensing applications. And this is the two photon interferometry. This is what you should expect. In fact, the coincidence count should satisfy this relation. Again, this black one is the theoretical one, and the red one is your experimental one. And as you can see, there is a matching between this theoretical value and experimental value. So therefore, you can say that the single photon interferometry and two photon interferometry which you have realized in your lab, we have also used this setup for sensing application. In fact, we have some preliminary results where we have used this experimental setup for sensing some glucose concentration. I think I will take another 2 minutes to show this slide. It may be also interesting for some of you. So just you can see this slide.
How we produce this heralded single photon in this setup. So this is basically this pump laser source which produces 405 nanometer wavelength, and then this is sent to this PPK crystal, and this is the PPK crystal which is connected to a temperature controller. You can also change the temperature to produce different wavelengths. Now, once this wavelength is produced from this laser, then this is volumetric to different stages, and it is sent to this beam splitter, and then after this splitting of the beam, it is allowed to pass through different stages, and finally is incident on this PPK crystal. PPK crystal, there will be two down converted photons, as you have discussed. This pump signal is down converted to two photons. One is signal photons and another is idle photon. And these two photons are separated by another beam splitter. And as you can see, this idler is allowed to pass through different stages and finally to this detected single photon counting model. You can see this single photon counting model here. So these are the two single photon counting model known as SPCM. So when these two signal and ideal photons are produced from this stage, one will come to this and then it will pass to this optical fiber and is connected to one of these SPCM. And the signal will pass through this different stages, and finally will be connected to this another SPCM through another optical fiber, and the output of this SPCM will connected to this timetable, where we can count this coincidence. So the coincidence can be measured using this timetable with a given time frame, and this is again connected to this computer where there is a software, and you can calculate how this coincidence count changes with the different time. So it show how actually the coincidence count changes with time, and how this heralded single photon can be estimated. When this time delay is equal to 0, then you should get a maximum coincidence count, and this will signify the heralded single photon. So it will show how this heralded single photon is possible using this setup in this computer. How this.
So I think now I think this is all about the presentation. I think I have already crossed the time. Time is okay. So let me conclude. Any questions? If you have, then you can ask.
I have two questions. So thank you for a very interesting and informative talk. Yes. Since you are increasing in sensitivity by using photons, so in this case, detector will react to unwanted noise sources. So how do you distinguish whether it is desired noise or non-desired noise source?
No, actually, I think your question is how I am accounting for the noise, right?
Yes, because since you are increasing the sensitivity, and it will react to very little noise also. And see, how you are going to distinguish?
These sensors, actually quantum sensors will be applicable when this power level is low. Classical sensor will be preferable when this power level is high. So when you are decreasing this power level, then actually the noise will be dominating over the signal. So in that case, the problem will be there. So therefore, if you are using low power, then you have to use this quantum sensor. If you are using high power, then you have to use these classical sensors. So therefore, in this case, you are using low power. So because you are using low power, then you cannot use a classical sensor because this noise will be much more than the signal. Therefore, everything will go wrong. So therefore, if you are decreasing this power, then the SNR, as I mentioned. So SNR actually is dependent on the value of this root of n. So if you use classical sensor, this will be something 1 divided by n. Root of n, for example, root of n, not n, root of n. If it is quantum, this is less than of root of n. The numerator being same, that is the average number of photons. So therefore, this SNR will definitely be less in case of your quantum sensors.
Okay, thank you. My second question, could you inform the type of detector used by you and its efficiency for quantum sensing?
These are the single photon counting modules. As I have mentioned in one of my slides, I have also shown the specification there. So these are the this is actually the detector we are using, single photon counting module, and this is SPCM 840FC. So these are basically this detector for single photons. You cannot use ordinary detector for counting these single photons.
Yes, but what is the efficiency? Is it 95% or 80%
Oh,
or and so on?
oh, you are talking about the efficiency. Efficiency is something 84%.
Okay, thank you.
Sir, I have a question, sir.
Yes.
So this may be more basic nonlinear optics, because I know that in nonlinear optics, when you have a nonlinear crystal, it generates actually second harmonic, right? We
Yes.
have a frequency omega in the input. In the output, we get omega and 2 omega also. But what we are saying is something different. We have high energy photon that is generating 2 down converted photons. So
Okay.
is it a Chi2 effect, or what is this actually? Because second
This
harmonic
is
is
actually
a Chi2.
second harmonic generation. Actually, see, the output will contain also the signal. Sorry, the pump. But the pump actually is coming straight, and you have to block this. For example, if you have, for example, how many actually SPDC will be produced? For example, in 1 million, maybe you will get 100 SPDC process, and other photons will go as such without any SPDC. So maybe out of 1 million pump photons which you have used, you will only get 100 or 200 SPDC process. And again, the pump photons which will come out, you have to block. I have not shown in the diagram. In fact, if you will see here, this one. Yes, actually out of this, this is actually the 2 photons, right? Which are, this is signal and idealer. Beside the signal idealer, also the pump photons will come out straight, and we have to block them. So you have to block this, pump photons. Pump photons are also coming along with the signal photons and idealer photons. So that you have to block.
Thank you.